This is Dr. Tesler for Operating Systems. This is in the 5th week of our course where we'll be discussing threads. There have been several questions relating to threads and how they differ from processes, so I'm hoping by the time we're through this lecture you'll have a clear understanding of the difference of a thread and a process, especially from the perspective of an operating system and as a developer. So just to make sure that we're covering our bases from our last lecture, make sure that you understand the notion of a process and the life cycle of a process, from running, waiting, starting, terminated. You should be familiar with those concepts before proceeding. Also remember the basic concepts of IPC, what it means for inter-process communication, the models of those methods, and how they might be implemented in the operating system themselves. In today's lecture, we'll give an overview of what we're going to cover, discuss multi-core programming, threading, the libraries, what implicit threading is, and some threading issues. The operating system examples will be a little lighter. To just reiterate our objectives, we'll be discussing what a thread is from the perspective of a unit to execute upon the CPU, and how that comprises a multi-threaded application. We'll talk about the APIs for multi-threaded programming, including pthreads, the Windows thread library, and Java's native thread support. And then we'll look at some of those issues with multi-threaded programming. There are some areas that we will not explore. Those have been grayed out. You can see them in the slides when you download them, and you can find more information about those topics in the book if you're curious, and then you'll need to continue doing your research outside of the book if you're really interested in those techniques. So why multi-threading? Modern applications are multi-threaded. Well, that's not really a motivation, that's just a statement. We need to understand why they're multi-threaded and how they run within an application. The basic idea is that a multi-threaded program can do more with less, meaning that it needs fewer processes that take up and consume more system resources than multiple threads would. Additionally, sharing information between threads is much easier and lightweight compared to IPC between processes. And this allows applications to be a little bit more flexible, that the different components of an application may be separated by threads. One of the examples that the book likes to rely upon is that of a web browser, and one thread may be tasked with updating the display for a tab, while another goes and fetches network information. Another one might be spell checking in a text box, and then another might be responding to yet another network request. So the application may divide itself to provide individual services, and when we compartmentalize aspects of our application, including execution, we gain modularity and maintainability. Compared to a process, then, a thread is much lighter weight, especially when being created, and kernels themselves have adapted this modular system to be multi-threaded in some cases. So what is a thread? We discussed threading running within an application. We're not quite there yet, and we call it a basic unit of CPU utilization. That terminology the book uses, I'm not particularly fond of it because utilization has a specific meaning. What they intend to say here is that this is what a CPU does, is that it executes instructions. And executing instructions may go sequentially, one after another, or those instructions may branch as you've programmed in your individual applications, where one instruction may execute, and then following the condition of an if, it will take the positive or negative, the true or the false path through that if. So we say that flow, a control flow, is execution, and the processor executes that flow. So that's the basic unit, is that a CPU is there to execute an instruction and then adjust the flow through the remaining instructions. This is more easily, in my mind, it's a little easier to consider a program without branches first, and how a processor operates is that it executes one instruction and then it moves to the next instruction in memory. So that flow would be serial. Execute one instruction, move to the next address. Execute the next instruction, move to the next address. And that increment of the program counter moving to the next instruction, that's a native property of the processor. You don't have control over that in your program typically. However, there are other instructions which change the address of the next instruction. So that part of your if will include an instruction that says when the if condition is false, move the instruction counter to another location in memory. So that is what we call the unit of CPU utilization is CPU execution, is that there's a control flow through a process. And that control flow, there may be multiple control flows within a process, but each one of those is a thread of execution. So more formally, a thread has an identifier that says this is a thread. A program counter, that's where it is in the memory space of the process where it's executing, a set of registers, which corresponds to the CPU state, and then a stack, which holds the local parameters that have been, the local variables that have been created while making function calls. So threads within the same process share the same global data to the process. From our previous lecture, that includes the source, the code, the text section, the data, and the open file handles, and maybe any other devices that are open. To illustrate, on the proper slide, let me take myself out of here, and let me get a cursor. So on the left, we have a single-threaded process. And this comes from our last lecture, where we had a code segment, a data section, segment, open files, maybe open devices, any other resources that the operating system associates with the process, then a set of registers which represents the process state of the single thread of execution when the task was put in a waiting state, removed from the processor, and then a stack which represents the local variables on the function call stack, on the call stack. And there's this one thread of execution, and that's our single-threaded process that we discussed in the last chapter. The model that we're moving to is a multi-threaded process, where the code, data, and files are shared among the multiple threads within the process. So each thread has its own register and stack, and then its own program counter. This allows the processor to select an instruction from one thread and begin executing there. And at some point, that thread might be suspended, might be placed in a waiting state for a thread, and the operating system could select another thread within that process to execute. And that's just one model of how execution of those threads might take place. Otherwise, the user may implement their own threads of execution as well. So the important piece to take away, though, is that there's a program counter associated with each thread, as well as the registers in this stack. And that allows the CPU to execute that flow of control over the code segment, because the code segment is shared between all threads within the same process. So what are the benefits? We've discussed some of them so far, but some of the other ones that may not be as obvious are responsiveness, that if we were to have synchronous communication in one thread, other threads could proceed while that thread is blocked, waiting for that synchronous communication to complete. Resource sharing is a large benefit where the code segment doesn't have to be loaded into memory, neither does the data nor the open files. And again, economy, this is same as resource sharing in almost a way, but this time in processing time, that context switching between threads is much less expensive than context switching between tasks. And in systems that have multiple processors, those multiple threads may be executing on distinct processors and therefore running faster, getting their job done. One of the models for multi-threading is that a client makes a request to a server, and that server is multi-threaded instead of being multi-process. So again, the web server is the one the book uses consistently. A client would make a request of a web page, and upon receiving the request to open that socket, and begin communication, the server would send that request to a thread instead of handling that request in its own thread of execution. Thus, that allows the server to dispatch the request to the thread and continue listening for incoming client requests. And when each client makes a connection, send that request to a thread to be serviced. And so this leads us to multi-core programming or multi-threaded programming. And there are many difficulties in developing a multi-threaded or multi-core application, and that's dividing those activities. How do you separate your task? How do you balance work between them? Where do you send data? If one thread can work on, if in your previous application one thread worked across all of the data, how do you divide that among other threads? How many threads do you need? And then testing and debugging in this new environment with multi-threads of execution is much more difficult because debuggers still take that perspective of debugging a single thread of execution. So there's a distinction between parallelism and concurrency. Parallelism says that the system can perform more than one task at a time. Concurrency allows tasks to progress concurrently, though maybe not in parallel, and that's a little difficult. There's a better slide coming up that will take a look at this. But what that means is that one thread might progress but doesn't have to complete before another thread may progress. So one thread is executing concurrently, meaning that it's not yet terminated. It's been ready to run, it's done some execution, now it's waiting, and another thread can concurrently execute. It can go and do some work before returning to the first. So we have a better slide of this coming up, but just try to separate the idea of parallelism. That means that two things are happening at once. Concurrency means that two threads of execution are progressing after some amount of time. So there are different types of parallelism, and that says that data can be sent across multiple cores, and that you perform the same operation on each. So you can think of this as you run the same code across different data sets, such as multiplying or adding matrices. The row-wise addition or row-wise multiplication, that's the same operational set, the same instructions, but the data will change depending on which row you're executing. In task parallelism, different from data parallelism, the conceptual operations take place across different cores. So data parallelism, multiple cores running the same code across different data. And that might be each core can participate in an addition of a matrix, but only a subset of the data from it. Task parallelism may say, I'm going to add two matrices on one core, and that's its task is addition. But on a second core, the only operation it performs is multiplication. So there the tasks are separated, addition and multiplication, rather than the data being distributed. And this is well out of date, that 8 cores and 8 hardware threads per core is modern. We have Ryzen chips that sit on your desktop that have more cores than that today. So the motivation for threaded programming comes from the demands of computation that needs to have increased throughput. Image processing is a great example. And as a result, the hardware responds to the development techniques that developers are using to address these more complicated problems. So trying to draw that line again between concurrency and parallelism. If we look at time on the top graph, we have threads 1, 2, 3, and 4, and they are executing concurrently on a single core system, meaning that thread 1 executes, and from thread 2's perspective, it's also executing. It just needs time on that processor to execute. Instead of thread 1 executing all the way from start to finish, and it takes, say, 3 time units. So if this were not concurrent, if it were serial, then thread 1 would execute for 3 time units, followed by the 2 time units of 3, and the 2 time units of 2, and the 2 time units of 3, and the 2 time units of 4. Instead, they are interleaved. The task 1 runs for some amount of time on the processor, progresses. Thread 2 then takes its time slot, progresses some amount, etc., etc. They are concurrently executing in that they are concurrently progressing, though they may be waiting. Conversely, in a parallel system, thread 1 and thread 2 can execute on distinct cores and progress simultaneously. So they are executing in parallel, though not concurrently. Similarly, task 3 and task 4 are executing parallelly. So a parallel system is by definition a concurrent system, though the execution time spent on the processor happens simultaneously. Amdahl's law is something that we should consider when thinking about threaded programming. The specifics of this are very simple. We can distill all of this slide, and it does a pretty good job in the book, in saying that as you increase the number of threads in a task, the speed up that you will get is directly related to the amount of serializable code, meaning if some portion of your task cannot be parallelized, that is what will dominate its runtime as you increase the number of threads and the number of processors available. So for instance, if we have a shared startup segment that sets up our data, that will bound the distributed calculation of our particular task, and the task here is all the threads together. So the important thing to take away from Amdahl's law, and please read it in the book, is that at some point there is no benefit to adding threads, and there is no benefit to adding processors to address those threads. So there is a limit to how much benefit you can receive by increasing your threading count and increasing your processing count. We've talked only about threads in general. There are two types of threads. There are threads that the user would define, say, controlling execution on their own. And there are threading libraries that enable the user to create threads and execute code concurrently or in parallel, depending on the system. The APIs that we'll look at are POSIX, Windows, and Java, Java's native support. And then there are kernel threads. And those are threads of execution that are supported by the kernel, meaning that the kernel will dictate when those threads can execute on the processor rather than the task itself deciding when to execute one thread or another. From the application's perspective, it will use the same API, and whether or not the API takes advantage of the kernel threads for those user threads is up to the API. And all of our operating systems take advantage of this because there is support for threading on modern processors. How they support multi-threading may vary, and the models are many-to-one, one-to-one, and many-to-many. And this refers to the left half refers to the user thread and how it's related to kernel threads. So many-to-one, many user threads to one kernel thread, one-to-one, one user thread per kernel thread, many-to-many, meaning that there may be a distinct number of user threads from the number of kernel threads that exist. So the least useful is many-to-one. And this takes multiple user threads and has one thread of execution controlled by the kernel. This means that the individual threads cannot run in parallel, though they can execute concurrently. And so if one thread were to block, then it may block the entire process from completing any other of the threads within that process. So this is the least useful. The one that Linux and Windows uses is the one-to-one model, where every user thread corresponds to a single kernel thread. So when you create a user thread by the POSIX API, that makes a request to the kernel, which then creates a thread that can be run on the processor. And then this leads to this is nice and straightforward, easy to understand, and has greater concurrency than our many-to-one. But it does increase the overhead, because just as processes have overhead, so do threads. We saw that they have registers and stack. So as you increase the number of threads, then those resources are consumed. Lastly, in an effort to mitigate the cost of many threads, we might have a many-to-many model where there are a set of kernel threads that are executing, and some subset of those user threads are assigned to those kernel threads to execute. So in this case, up to 3 of these threads may be executing, meaning that they're queued and ready to go on the processor and sharing time. And eventually, when one of them terminates, the 4th will be picked up to execute in one of those kernel threads. And this allows the operating system to bound the performance of its threading so that only a certain number of threads are created, and limit the resource usage of a large multi-threaded system. And you might mix the two, asking that among our many-to-many model, that you select a thread that you want to have sort of a higher priority to make sure that it always runs and is assigned to a specific thread in that 2-level model. So this is what we have here on the left, is that many-to-many model with the 1-to-1 model on the side. And by description, by decree by the user, it says, okay, well, these 4 threads, they can map to any number of kernel threads, but this particular thread, I want to make sure that it's pinned to a specific kernel thread so that it always has an opportunity to progress. How users get their threads, and users here are programmers, are through an API. And there are 2 ways of implementing this. The first is by a library entirely in user space, and the other is this hybrid approach where the library in user space will make calls into the operating system to help get these threads created and assigned. pthreads is the most common one. It's supported on Windows and on Linux. And it is a specification, not an implementation. And what this means is that the pthread specification defines an API for user applications to request threads, to create threads, to execute threads, and to terminate threads, and any other management activities related to them. But the implementation is left up to the developers on that particular system. So again, it's a specification, meaning the API will stay stable, but the implementation may differ, meaning that on your processor that doesn't have support for threading, there may not be a reason to have operating system support for pthreads, so it would just be a user library. Where on a system that does have hardware support for threading, you may have an operating system facility to enable threading, and the pthread library would be tied to it. So the example that we'll use will seem fairly familiar to forking. And we'll take a look here. The first half of our example, what we want to pay attention to is the sum and then this runner. So this runner, this is where our new program counter is going to start, is the address of this function when we get to it. The main function sets up space to hold the thread ID, the set of attributes for the thread, and then does some error checking, some command line argument error checking. And then, pardon me, it initializes the attributes of the thread. Just for the moment, just think of this as something we have to do to get the API to work. And then we create the thread. And most importantly, we provide the runner function pointer to create, and in this case, some user data. And what this does is it creates a new thread to execute starting at the address, the starting instruction of runner. And it takes as one parameter the single command line argument that we gave it. So that's the important piece, is that we've created a thread and we've given it a starting point. And that starting point will give us a stack that's empty, except for the push of the parameter to the initial call, a program counter that sets the starting location to runner, and then the rest of the registers will be initialized to some value so that this code can begin running in its own thread of execution. So at this line here, we have one thread of execution, which was our main. After this returns, there are now two threads of execution, one for the main program, which continues executing here, and the second thread of execution begins at this line of source in our C file. So the main thread of execution does nothing except for wait for the thread to complete. In this case, we call this a join, meaning that the child thread, I apologize, I shouldn't use child, meaning the new thread has completed and has exited, so we get that back, very similar to waiting for a child process. When that is completed, then the parent thread just displays the sum. How we got that sum was in the other thread, was to take our upper bound, calculate the sum by adding the numbers together, and then exiting the thread. So the important pieces here are the concepts of the API that, oh, okay, we have to create a thread, and this particular thread, the main thread, is the thread tasked with managing the executing threads, so it waits for it, and then that signals that the job is done, that the thread's task has completed, and the sum is available. Sum is used in both the the first thread and the second thread, which was our global data. So we're sharing that global data. We're sharing the same source code because we've written it in the same file. And but there's no IPC necessary to do so. So there we go. That is how a user can create a pthread and do its execution, and perform execution in distinct threads. I apologize. And this would lead to more complex systems with modular code segments that might share information they may not if they're just dedicated to performing a small task. In the case where you might need to wait for multiple threads, in case we spawn, say, 10 threads, then we would join each of those threads one by one, waiting for them. For Windows, the API is similar, though it's just a little bit more verbose. So in our example here, for the same summation program, our shared data is our dword, our sum. That's a native size of a word on this particular architecture, which will be 32 bits. And here we're using the particular Windows API to denote the storage and symbols. So we have our Win API signature for our thread entry point. And here it passes a void, that is param. Param is a pointer to a dword, which we then dereference to get the value of the dword, which we'll then treat as a regular integer and increment it. So from the second thread's perspective, the only work is to start at the summation function, take its parameter, calculate the sum, and then return 0. And sum here is stored. It's global between the two threads. The main function performs a very similar operation to that of pthreads in that it checks its arguments and then creates a new thread. And here, create thread will also run the thread once it is created, starting at the summation entry point, passing the one parameter of param, and then gets the thread ID back. So we stored the thread ID as another dword. We get a handle, which is a Windows API data type. And that thread handle is assigned as the return value of create thread, and thread ID is set upon return. In the main thread, if the handle has been created, if it was successful, then it waits. This is waiting for the single object that is the thread handle for a particular amount of time, which in this case is forever. And that object is a thread. Once that thread completes, then it closes the handle. So again, how the thread indicates that it's done is by returning a value from the top level function. In this case, 0 indicates success. The return value is not what's used by the main thread. It is the shared global value of sum. So it prints that sum. In Java, threads are very different. They are first-class objects. They are defined as part of the JVM. And the JVM, if it lives on a system that has operating system support 4 threads, then that JVM process will use the APIs and the facilities of the operating system to create threads on behalf of the user. And again, the user here is the developer. There are 2 ways for the user to create threads. The first is by extending the thread class, and the second is by implementing the runnable interface. The more common is to implement the runnable interface, which simply says that the run method must be defined. So the example for this one is a little bit more complicated, and it's divided into 3 classes. In the previous 2 examples, the sum variable that was shared between the 2 threads. Here, in Java, we don't share information between threads. Information is isolated because of the object-oriented paradigm. And the Java developers and specification writers intentionally did so. The information that we're going to share is an instance of the sum class. So we're going to share a sum object. The thread that we spawn from our main thread will, upon construction, get a reference to a sum object and an upper bound to calculate. And then when the thread is created and started, it will begin execution at this run function. That is where the program counter will be set and the initialization for that run for the thread completed by the thread API and library. It is not the responsibility of the developer to invoke run directly. Doing so would make the execution of run occur in the thread of the caller. Instead, we need a thread created with its own register and stack and process counter able to be run independently, then run by the threading library or the operating system, dispatching it to a processor to execute. So this is our main thread, which is what you might be familiar with in your Java programming, that we have an entry point for our main thread of execution. It checks its arguments, creates a new sum object, giving us a sum object reference, takes that single argument from the command line, and then creates a new summation object, and that was what implemented the runnable interface, meaning that it can be run as a separate thread. That single reference to the summation argument is passed as an argument to the thread constructor, which gives us a new thread. At this point, the resources have been allocated for the thread, but it isn't yet ready to run, meaning that it's not ready to enter the running state, that it is not yet submitted to be dispatched by the scheduler of threads. To do so, a thread needs to call the start method on the object, which the main thread does here. And now the thread is off and executing, ready to run. It's executing concurrently or in parallel, depending on the system. The main thread here then attempts to join that thread that was just started, meaning it's waiting for that thread to complete. Once it does so, it knows that the sum object, the reference that it passed, has been updated by that thread, and the value has been calculated and ready to be displayed. If there is any kind of error running this thread, an exception will be raised. In this case, the main thread ignores it. So far, the threading models and so far the threading APIs that we've looked at have thread control explicitly managed by the user, by the developer. Increasingly, there's a desire to get out of management of threads, synchronizing data across them, sharing information. It's an easy way to introduce errors into your program. So instead, there's this idea of implicit threading, where the developer says, parallelize this section, and then the compiler or the library will handle creating threads, dispatching, sharing information, doing the tedium that could easily go wrong, and then just return control back to that first thread of execution. So the one that I'm most familiar with is OpenMP. We'll take a look at thread pools for Windows as well, though just briefly. And then Grand Central Dispatch is specific to Apple. If you're interested in that, please take a look at the book and other resources online you can find on your own, as well as the Java concurrent package. Threading in Java is usually sufficient, but if you're looking for something less onerous or more featureful, then you might want to look in that one as well. So our concept is that we have, there are different ways to implement this implicit threading. One is thread pools, and there the process of creating threads has taken place preemptively, that when the application starts up, it will create a set of threads that do nothing until they have work to be done. And so what this means is that threads will sit idle, not runnable, until there's a task to be performed. Then when that task is available, it will be dispatched to that pool. So the Windows API provides a pool call to creates a pool function, and then each of these code segments will run within that pool when one of those threads is available. So threads become long-living. They start with the application and they shut down, and dispatching work to those threads, not execution, is handled by the library. OpenMP is a very different programming paradigm in that it uses C preprocessor directives, and it's available for C, C++, and Fortran. And this is used in HPC occasionally, and it's geared towards systems that have shared memory. And the note here that it identifies parallel regions, that is that the user, the programmer, identifies parallel regions. So there are specific pragmas, these are preprocessor directives, these are text replacements, and it says, in this particular example, there's a for loop here, and please parallelize this for me, and the compiler then examines the next for statement to see what can be parallelized and sets up the dispatch of the code segment to different processors and splits up the data. So here, this is data parallelization, not task parallelization using this particular pragma. So the Windows API used a pool function that would dispatch that code to any particular processor that was available and any thread that was available to run it upon, whereas OpenMP in this example is separating the data across multiple threads, possibly across multiple processors. And then for task parallelization, this particular block may be a function call, who knows, that could be run across the multiple threads that are available. So here, again, threading pools, OpenMP, the basic concept is that thread management, create the thread, wait for the thread to complete, check the error status, those operations have been abstracted away from the user, and the user has this simpler API to define the parallel work that needs to be done. So with threading, whether implicit or explicit, there are some semantic issues and concerns with data sharing. So in particular, fork and exec there might be different concerns when you have threads already running. So in particular, what should happen when you fork if there are running threads? Should those threads be duplicated? What about exec? When you exec within your newly forked process, what happens to the old threads? Signal handling is an area we may not have touched on in too great a detail to fully understand the concerns, but one of the ones that we would want to worry about is the idea of signal handling delivery. So there are two types of signals that we'll refer to here. One is synchronous, one is asynchronous. And what this refers to is the origin of the signal. So a signal, even though it's in software, not hardware, indicates an event of some kind. Typically, they're not positive messages. So one type of a synchronous event is a memory violation. And that means that the process that's running has accessed memory outside of its allocation. And that causes the process to be killed immediately. That signal is delivered synchronously because the task was executing and that caused the signal to be raised. So the the process that raised the signal will handle it immediately. Asynchronous is from the perspective of the task receiving the signal, and that the task receiving the signal was executing, the process was executing, the thread was executing without issue, and another process caused a signal to be raised to the process. I apologize. I'll say that one more time. I'll try to slow it down a little bit. From the perspective of the process receiving the signal was generated outside of itself, that another process was running, and it in particular delivered a kill operation which sent a signal to this process. That process was executing whatever it was going to execute, completely oblivious to the signal coming in. So that's asynchronous. It refers to where the signal came from. Further, when a thread is canceled, how do we handle that thread? That's another issue. So a thread is executing and another thread requests that thread be canceled, be terminated. How do we handle the resources that are associated with that thread when we terminate it? And then there's this concept of thread local storage and what we will do when activating the scheduler. So to the first issue, fork and exec. If in one process a thread of execution calls fork, that fork request is for the process, not the thread. So should fork duplicate all the threads running or not? By default, Linux will duplicate the threads. And where this becomes problematic is, well, if I'm going to duplicate a process and then exec, in duplicating the process by forking, we've copied everything. Now, exec replaces everything within that process, including the running threads, so they would just be deleted. So it would be nice to be able to fork without creating those additional threads. So that's one of the issues that can arise, and how do you handle it? That's an per operating system decision. Linux has decided to copy on fork and then destroy them all on exec. Signals are not unique to Linux in concept, but the signal discussion in the book is specific to Linux, or Unix. It's Linux at this point. So the idea here is that some event occurs. Memory violation is one of those events. Another may be that there's an interrupt, Control-C on the command line. The process has a signal handler, and that is a set of code that responds to a specific event occurring, say Control-C or a memory violation, and those are provided to you by default. You may or may not have written a signal handler, so those default ones are provided usually by the compiler, by the programming library that you're using to build your application. And you may, at runtime, replace those signal handlers with your own signal handlers. So Control-C might not cause your program to exit. So using Control-C as an example, you're in the terminal, you're editing a file, you hit Control-C. The process will then receive that signal and has likely replaced it with its user-defined signal handler, which will tell it to do something else like copy text. In a single-threaded application, there's only one possibility for delivering that signal that goes to the only thread of execution to handle it. However, for multi-threaded applications, where does the signal go? There are multiple ways to handle this problem. It could, if it were a synchronous signal, it could be delivered to the thread which created the signal. For an asynchronous signal, the operating system may try to determine which thread is the proper one to deliver the signal to. Or the signal might be delivered to every thread in the process. The thread might be delivered to only a the signal might be delivered to only a select number of threads, or the user might be able to specify that the threads that receive those signals. And as a reminder, signals are delivered in software. They are a request through the operating system. So the operating system delivers that signal to the processes. And the policies to apply that are going to be those are going to be defined by the capabilities of the operating system and the APIs that sit upon it. Thread cancellation is another responsibility of possibly the operating system, if not the threading library. And this asks that a thread be stopped before it's actually finished its work, before it's returned or its pthread exited, before the operation that thread was dispatched to perform has been completed. And the thread being canceled is called the target. And asynchronous cancellation, here this means asynchronous and deferred indicate when the cancellation occurs. Asynchronous, the target thread immediately dies, the resources are released. Deferred lets the thread runs to a good checkpoint where the information, the resources can be released. So in the pthread library, when you want to cancel a thread, you do it by the task ID, and you have options in asynchronous or deferred cancellation. The default is deferred, which is the set of is set as one of the attributes. Did they set it here? They did not. So you can change this to being disabled, meaning that you can't terminate, you can't cancel a thread, it must complete, or you can make it asynchronous, meaning it stops immediately. And the way that a thread will reach a checkpoint is to issue the test cancel function call within the thread, and this says, I'm at a good place where I can be canceled. And the piece that you can't quite see here is that on Linux, thread cancellation is handled through signals, meaning the operating system, because it's running kernel threads, will deliver a signal to the thread to cancel it. So thread local storage, you may have heard of this in other operating systems referred to as task local storage, TLS, separates data between threads. This means that this is local state to a particular thread, and this differs from information on the stack. This is similar to global data, but it's global to the thread, not to the process. So this way, you can say, all right, I need to allocate a specific amount of state and have it available to all functions within a particular thread, so we will allocate some thread local storage for it. Now that we've sort of covered, so one last thing about threads is that we have this dichotomy. We have the kernel thread and the user thread. And there's a tie that binds the two, and sometimes that will be called a lightweight process. So there's a data structure in the kernel that holds the information for the thread that is related to the user thread. And moving this lightweight process, rather than a whole process, to an area to execute is part of activation. When do we execute? So what the activation here is trying to identify a different type of scheduling decision between a process scheduling and thread scheduling. And here, because we have kernel threads which map to user threads, and it's no longer this one-to-one mapping, and we have those different models, now we have to figure out where to move that user thread to then execute in a kernel thread. And that is what the lightweight process is for. And just think of this as the data structure that binds the two together. That's the easiest thing to keep track of here, is that there's got to be some piece that ties my kernel thread where it's executing to my user thread, which is this other concept, and it's that lightweight process that joins the two. And as an operating system decision, you need to decide how many of these lightweight processes to create, and that will that in one-to-one, it's already finished. You got one for every user thread and kernel thread. But in many-to-many, you will have a certain number of lightweight processes that are pre-described based on how many resources are available, and you will need to make that decision at possibly at runtime or compile time, but that number will depend on what's available on the system and what you can handle. So that's the glue that binds. The decision on how many lightweight processes are necessary only applies in the many-to-many model or in the tomb level model, which is also many-to-many. So that is the purpose of a lightweight process. So just to revisit, we have as our objectives for this lecture is to understand what is a thread, and then just describe the APIs available for users of threads on a system. And then what is implicit threading, not necessarily how we might implement it, but what we can use. And then talk about a couple of the multi-threaded programs, multi-threaded issues, such as duplicating threads in fork and signal processing. So I look forward to your questions on the discussion board, and I will see you in the next video.